Okay, well, I hope you are all doing well. Hope you had a good holiday weekend. We'll get started in chapter 4 today. Okay, chapter 4 covers correlation and regression analysis. Correlation. Regression analysis. Okay, if I had to kind of divide statistics, the subject of statistics into, broad categories, I would put correlation and regression analysis still under the umbrella of descriptive statistics. Okay, so part of our unit on descriptive statistics. Okay, because so far we have covered describing categorical data. That was kind of in chapter 1 and part of chapter 2. Chapter 2 is all about visual displays. So we just learned how to describe categorical data. We use frequency tables, two-way tables. We've learned how to describe numeric data using histograms, box plots, dot plots, and also using the numeric summaries, the mean and the median, and describing its spread, the standard deviation, and IQR. Okay, so we've learned how to describe categorical variables and describe numeric variables. With correlation, we are describing the relationship between two numeric variables. Okay, so with correlation, oh, you know what? Let me pause for a second and dim the lights up here. Okay, so all right, and let's see. So with correlation, we describe the relationship between two numeric variables, and so it is key that that we're talking about a relationship, and it's also important that we are talking about two, and that they are numeric variables. Okay. Okay, so for example, we could talk about is there a relationship? So let's say we collected data on a bunch of snakes. Okay, we collect data on a bunch of snakes, and we'll say they are all one species. Okay, and yeah, all right. So here's my lovely picture of here's one snake. Okay, and then here's another snake. Okay, and you don't have to draw the snake in your notes here. Okay, and so the question is, is there a relationship? If you had to predict which snake weighs more, we're going to ask, is there a relationship between the length of a snake and its weight? Question. Okay, is there a relationship between the length of a snake and its weight? And what would we say? Overall, we would say this snake is too fat. Let me. We would say yes. In general, we would expect that a longer snake will weigh more than a shorter snake, okay? So we would say, yes, we expect a longer snake to weigh more than a shorter snake. Okay, and this is pretty much what correlation and regression is all about, okay? We're just picking two numeric variables and we're asking, is there a relationship between these variables, all right? And so with the case of snakes, it seems very obvious, like at least if we're talking about the same species of snake, we're all expecting them to be about the same kind of thickness. And so we would expect longer snakes to weigh more than shorter snakes, okay? And of course, there might be, kind of exceptions. You might find two snakes where one is longer than the other, but it actually weighs less than another, and things like that. But it doesn't have to be snake length. We can talk about, what two things, two numeric variables that are, other two numeric variables that are related. We could talk about, as far as people, we can say, is someone's waist size related to how much the person weighs, okay? So waist size would be one numeric variable, and the weight of the person would be another numeric variable, okay? We can see if there's a relationship between someone's annual income and the value of the house that they live in, okay? All right, we would probably expect some kind of relationship where people who make more generally live in more expensive houses, but there's always going to be exceptions, right? Like Warren Buffett, one of the richest people in the world, still lives in his original home that he bought, like 40 years ago or something, 50 years ago. So we have different things, and we are going to learn how to describe the relationship between two numeric variables, okay? So this is kind of just a very loose description, and we will, just like everything else, we'll formalize it, and then we'll attach numbers to kind of quantify the relationship and things like that, okay? So this is kind of just a simple way to describe a relationship. Okay, and then, so we'll say later in the chapter, we will, kind of learn how to formally describe a relationship between the two numeric variables. Okay, and we will also try to kind of, what we're going to say, model the relationship with an equation, okay? So that, right now we're just saying longer snakes are going to weigh more than shorter snakes. Later on we might be able to say, if you have a snake that's 2.5 feet long, we're going to predict that it weighs this many pounds. If you have a snake that's 3 feet long, we can predict that it's going to weigh this many pounds, okay? And so that's going to be modeling the relationship with an equation. So this is kind of the big picture idea behind chapter 4. And so we'll we'll start with formally describing such a relationship, okay? Okay, and so kind of our first tool, the tool for looking at relationships. Okay, so the first tool we have is the scatter plot. And with a scatter plot, you are basically creating coordinate pairs of your data. Okay, so let's say I don't know. Let's say we're going to look at a bunch of different houses, and we'll say how many bedrooms does it have, and how many closets are in the house, okay, or dwellings, so maybe apartments and things like that. And so what would we expect to see? We would expect to see places that have lots of bedrooms. Will they have more closets or fewer closets than places with few bedrooms? In general, more, right? So okay, so we'll say maybe we looked at a one-bedroom apartment and it had 2 closets. Maybe we looked at a 2-bedroom apartment and it had 3 closets. Maybe we looked at a house with 3 bedrooms and it had 4 closets, and another house with 3 bedrooms and it had 5 closets, and a place with 6 bedrooms and it had I don't know, 10 closets or something like that. Okay, I'm just making this up. So we would plot this, and so on one axis we'll put bedrooms. We'll put X here, and we'll have 1, 2, 3, 4, 5, 6, 7, and on the Y-axis we'll put closets. Okay, and then so I'm just going to plot this. So the first one, we have the kind of the coordinate pair 1, 2, and then I've got 2, 3 right here, 3, 4, and I also have 3, 5, and I have 6, 10. So something like this. Okay, and so these are, I don't need to label every single one of these dots, right? And so, you know, here we're just kind of plotting these, and we can imagine, you know, I'm going to just start making up dots, and so maybe we have, you know, another one with so I'm going to put like another dot there, and maybe we have places with 4 bedrooms and they have this many closets, and 5 bedrooms they have and 6 bedrooms, I don't know. So we're looking at different places with different numbers of closets, and we're getting all these different dots and things like that, okay? And so, you know, here I'm kind of getting this grid because you can only have a whole number of closets, but, you know, we still see some kind of general trend where you have lots of, in general, you're seeing this trend where places with more bedrooms are going to have more closets, okay? So okay, something like that. All right, or another, we can maybe you are in the market to buy a used car or something. Let's say you want to buy a Toyota Corolla or something like that, okay? And so you go on different websites and you're looking at cars, okay? And you want to see, and then you're, so we'll say, is there a relationship between the mileage on the car? So we'll say, we're looking at a bunch of Corollas, okay? You're going to look at the mileage and the price, the asking price for the car. And I have no idea how much. So let's say there's a car that has 65,482 miles on it, and I don't know how much a Corolla with this many miles would sell for. $12,000? Huh? 6? How? 5,000? That's 6. 12,000. What's no? You'd like a new Corolla is like 20 grand, right?
What year?
I don't know. No, you don't know the year. It just says the mileage. Okay. This is all. This is the only bit of information you know. Okay. So you're saying 6,000? Okay. All right. Fine. We'll put that. We'll say someone's asking 6,000. Okay. And then another place has 20,402 miles. Okay. How much? This one is going to be asking for. Maybe another one has only 3,000 miles on it. 3,005. All right, and then so we're just making up numbers. So what do you think this 20,000 car with 20,000 miles on it? You don't know the year. You just know the mileage. 9,000? I feel like we should go on CarMax and look at these things. Okay, 3,000 miles. 12,000? Sure. Okay. All right. And then we'll, whatever. Okay. We'll just say more data needed. Okay. And then, and what we would see is we would see probably some kind of trend where as the mileage increases and we're looking at the price, you're going to see this trend where overall I don't know, some kind of downward trend where you have more mileage, the price that they're asking for is going to go lower and lower. Okay. Again, yeah, there are lots of factors that go into determining the price of a car. One being the model of the car, but we took care of that by saying we're only looking at Toyota Corollas. But yeah, like you said, there's other things. Was it in an accident? What year is the car? Things like that. These are the different things that that affect it. But we're just here as far as chapter 4 goes. We are just looking at the relationship between one of the variables and one other variable. Okay, so we are looking at 2 numeric variables, and that's it. Okay, so we are looking at just 2 numeric variables. Okay, and as far as trying to decide which variable you should use to, it's a tough question, right? Do you want to just know what year the car was manufactured? That will give you an idea, but you could have 2 different cars manufactured in 2014, where one's completely beat up and has 100,000 miles on it because the person used it as an Uber every day, or well taken care of, and it's hard to know all of these things. Okay, which variable's best? But you might see some kind of relationship like that. Okay, so these are examples. This one up here, we would say the direction is a positive direction or positive trend. And down here we have negative direction or negative trend. So you can label these as such, and let me kind of define these. Okay, so what does it mean? So when we're talking about a relationship, we need to talk about the direction, also called trend. Okay, and so we have a positive direction. Positive direction means that as one variable, or we'll say large values of one variable are associated in general with large values of the other variable. Okay, so I'll say large values of x are generally associated values of y. Okay, so length of a snake and weight of a snake. Snakes with large values of length in general will be snakes with large value of y. We have a question.
Yeah, can a negative trend also be called a reversal?
I have not really heard of that term reversal used in the context of linear regression, so I mean, perhaps, but not, in my experience, we generally say positive trend or negative trend, but okay, so we've got positive direction, large values of x is generally associated with large values of y, and we would say small values of x are associated with small y. Okay, so that would be positive direction, and then negative direction, we would say large values of x are associated with small y, and small x will be what? Large y. Okay, so in positive, large x goes with large y, small x goes with small y, and in negative direction, they're flipped around. Okay, large x goes with small y, and small x goes with large y. Okay, so as far as positive direction, you generally have something that looks like that, and negative direction, you have something that looks generally like that. Okay, so if just kind of so this would be positive direction. So, on the axis we have small x and large x. And over here we would have small x and small y and large y. And we can see that, if we look at the data, the small x goes with the small y, and over here, the large values of x go with the large values of y. Okay, so that would be the positive direction. And just the opposite for negative direction. Okay. Small x over here, large x over here, small y down here, and large y up there. Okay, and this would be negative direction. And what do we see when we look at the data? We see at small x, small values of x, we're associated with large values of y. And at large values of x, we have small values of y. So here, we are talking about the direction of the relationship. Okay, let's now talk about the strength of a relationship. Okay. As far as the strength of a relationship goes, we can say things either have a strong relationship okay, and so if the relationship is strong, then that means in general we see little scatter around a, quote unquote line. Little scatter, or we can say we can make fairly precise predictions for one variable if we have the value of the other variable. And then the opposite of strong would then be a weak relationship. And here we would say we see lots of scatter. Okay, and then our ability to make predictions is not as good. Ability to make predictions based on one variable is not very good. Okay, so as far as strength goes, something that looks like this . Okay, this would be strong. So you can have a strong relationship whether it is positive or negative. This would also be strong if you have a line that looks like this, or not a line, I should say, if you have data between x and y. Okay, both of these are strong because we see little scatter, and if I said, here's one particular value of x, make predictions for y, your predictions for y would all kind of be in this little zone here, okay? Whereas over here, you might have still some kind of relationship between x and y, but so here we still have overall a positive relationship between x and y, but the relationship here is weaker. Okay? And if I gave you, this particular value of x, and I said make a prediction for y, we see I have lots of scatter, and your kind of prediction zone is much bigger. Okay, so you're kind of your predictive ability is not as it's not as good. Okay, does this make sense here? So we'll take a look at some of these examples. Okay, and then and lastly, the thing we want to talk about when describing a relationship is the shape of the relationship. So we say a relationship, as far as this class goes, we're going to say either things have a linear shape. Linear shape means the general trend, general or overall trend can be summarized with a straight line. And then, and if it's not linear, we're just going to say non-linear, okay? And now in a more advanced class, you might have polynomial, quadratic, or exponential, or you would further divide up nonlinear into other shapes, but we would just say, as far as this class goes, it's either a straight line or it's something else, okay? And we'll say a straight line is not sufficient to describe the relationship. So we might say, you can have lots of scatter and still overall have a linear relationship. Okay, so here we would still say, overall, we're looking at something where, maybe a straight line seems to make sense. Okay, so this we can say is still linear, whereas you might have something like this, or something that looks like that. So these would all be nonlinear. So in this case, you would need something that looks like this, or in here you got kind of this funnel. So, in this class, we're only going to deal with linear trends, okay? So we will learn how to describe linear relationships only. Perhaps in another class, you would learn about the other shapes. Okay. Yes, question?
When you have linear and nonlinear, can it still be like strong or weak? Or do you only have to pick one characteristic?
So when we talk about strong and positive, those things really only make sense when we're talking about linear relationships.
Right. So
okay.
like with that linear one, would that be, that's a strong linear, right?
So it's either, we're just going to say linear or nonlinear. The strength is how much scatter there is, and so we would say the one on the left here, I'd say, yeah, moderately strong. There's some scatter.
So you can still technically, if it's a weak, like, scatter, it can still technically be linear, right?
Yeah, linear just means overall,
There's a general
does
direction.
a straight line make sense?
Yeah.
Okay, does a straight line kind of make sense? And if the answer is yes, um, then yes, we would still say it's linear. Okay.
Or,
I'm sorry.
oh, I just, good.
Okay, cool. Sorry.
There you go.
Okay, yeah, and anything else we're just gonna say is nonlinear, doesn't work. Okay. Okay, so kind of just to recap, when describing a relationship between two numeric variables, or we describe the direction, the strength, and the shape. Okay, and so to decide, so first I'm going to just talk about the shape. So to decide if something is linear or not, to decide if the shape is linear or not, the best tool is the scatter plot and our eyes. Okay, I mean, there do exist, you know, kind of formal statistical tests to decide if something is linear or not. But really, our eyes are very good, or, you know, our brains have developed in such a way that we're very good at detecting patterns to decide if things look kind of like a straight line or not, okay? You know, and that's why you can look out the window as you're driving past an orchard and you'll start seeing all of these lines with the trees, and you look at different things and you start seeing these patterns. And so, you know, you create a scatter plot, okay? Because if you don't create a scatter plot, all you're going to have is numbers, and your eyes are not good. You know, our brains aren't very good at just looking at numbers and deciding if something is linear. So we look at this and we'd say, yes, linear, okay? And then, you know, we look at something, something that looks like this, and we have a little bit of uneasiness saying that this is linear, right? It's like kind of sort of linear, but there also seems to, like, we detect a bit of a curve here, right? Okay, so, you know, a little, you know, this is what's going on, okay. So we say, you know, a little curved. So we might say linear is probably not the best. Okay, and we'd probably say, you know, it's safer to say nonlinear. All right, and so anyway, to reiterate is that, you know, always make a scatter plot. Always make a scatter plot. This should be kind of your first step in data analysis for two numeric variables. Okay, and so I'm going to introduce this concept of correlation, which assigns a number to the direction and the strength. Okay, so just like before when we had the standard deviation and the IQR, those are numeric summaries that give a number to this concept of spread rather than just saying lots of spread or little spread. Okay, Baker family children, lots of spread in ages. Adams family children, little spread in the ages, or whatever it was. Okay, rather than just saying lots of spread, little spread, we said standard deviation is this number for this family, and standard deviation is this number for that family. Same concept here. Okay, we're instead of just saying the strength is strong or the strength is weak, we're going to have a number that says this is exactly how strong the relationship is, and this is how, or this is how weak the relationship is. There's going to be an actual number there. Okay, and then that number will also tell us the direction of the relationship. All right, but again, as far as the shape goes, we don't have a number at this point to just say this, linear yes or no. Okay, our best tool for deciding if something is linear or not is to create a scatter plot and then to look at it. And I'd say our eyes are very good at detecting this. Okay, is that all right? Okay, so the number is called the correlation coefficient. The correlation coefficient. This is a numeric summary that assigns a number to the direction and strength of a linear relationship between two numeric variables. Okay, so again, it's just a way for us to assign a number to the direction and strength. Okay, and so the symbol we use is the lowercase r, kind of like relationship. Okay, and r can take on any value between -1 and +1. Okay, so if you get an r outside of that value, then something is wrong. Okay, or if you see something like 2.3, that that's definitely not going to be correlation. Okay, so anything between -1 and +1, that's going to be r. Okay. The sign of r is the sign of the direction. So positive r means the direction is positive, negative r, r greater than 0 means direction is positive. Oops. And r, less than 0 means negative. Okay, and then if r is close to 0, the relationship is weak. And if r is far from 0, so that means close to 1 or close to -1, the relationship is strong. Yes, question.
Yes. So would you say then maybe plus minus 0.5 would be the indicator of whether something is strong or something is weak?
I would not say that. Strong and weak is all relative, and depending on the context that we are dealing with. So it's hard to it's hard for me to just draw kind of arbitrary lines and say this is strong, okay, or this is weak. But if I had to, I would say probably 0.8 would be a better indicator. 0.8 and higher would probably be on the stronger side, and less than 0.5 I would say would be on the weaker side. But that's don't write those numbers down because it's all relative, okay? So you kind of just eyeball things. Okay, so this is what R means. Yeah, another question.
So if your R value is outside -1 and 1, does that mean that you need a calculation error, or does that mean that the correlation doesn't exist?
It means you've made a calculation error or something, okay? It's not, based on what the formula is to calculate R, it is not possible to get an R value greater than 1 or -1, okay? And in fact, okay, so let me just say a few things here, okay? These interpretations of R only make sense if the relationship is linear. Okay, R is just the result of a formula, so it does exist for nonlinear relationships. It's just that the value will no longer carry any meaning, okay? Can be calculated. So you can calculate, like, you can throw data into the thing and say, give me the value of R, and it can calculate a value. It's just, if it's not a linear relationship, it's not going to have any meaning. How do we decide if the relationship is linear or not?
Eyes are scatter plot.
Yeah, we use our eyes looking at a scatter plot, okay? That's how we decide if something is linear or not. Okay, so a couple other things about R. You are not responsible for learning the formula for R or calculating it yourself by hand. For learning how to calculate R manually. Okay. R, the correlation or R is almost always calculated with a computer or calculator or something like that. Is almost always calculated with a computer. In modern times, okay? to do it by hand is just kind of a silly, tedious practice, okay? Especially if you have more than 4 or 5 data points. So we're not going to bother with that, okay? So as far as problems in this course go, you'll be provided the value of R, okay? So you will be given R in the problems. Okay, so let's, so those are just some notes. And again, these are the interpretations for R. If the direction of R, or I'm sorry, the sign of R is the direction of the relationship, and if R is close to 0, the relationship is weak, and if R is far from 0, the relationship is strong. Okay, so let's just go through a few examples. Okay. Okay. What do you think R is in this example? R is equal to 1, positive 1. Okay, because you have a positive direction, and if we were to draw a line, and just draw a kind of a, there's no scatter about the line, okay? Or my intention is for it to be, you know, the dots to be perfectly aligned, so there's, you know, no scatter. Okay, and so, you know, one example was, you know, here we can measure the height of some person, height in inches, and we can just convert that height into centimeters. All right, and if we think about the definition of strength, one was how well can you predict the other variable if you're given one variable, okay? And so if you're given someone's height in inches, you can predict or calculate that person's height in centimeters perfectly, okay? And because you can make perfect predictions or calculations, your R is 1. Okay. Another example, this was, I'm just taking this from our textbook, is you might have something that looks like this, where you've got a little bit of scatter. What we're looking at is we're looking at the life expectancy for men. We're looking at a bunch of different countries. Each country gets its own dot. Life expectancy for men, and then life expectancy for women. And then, so, you know, this might be, I think the country with the highest life expectancy for both men and women, I think, is Japan. And so, you know, this might be a dot for Japan, and then, you know, the United States has pretty good life expectancy maybe around here, where, you know, the average life expectancy for, or the life expectancy for men is pretty high, and life expectancy for women is pretty high. And if we go to other nations, we might see lower life expectancy. And so, you know, if you're given the life expectancy of one of the sexes for a certain country, you have a pretty good idea of the life expectancy of the other sex. Okay, it's just that, you know, there will be some differences, but you can make pretty good predictions. We have an overall positive direction, and so you have R something like R equal to 0.98 in this example. Okay, so positive, very little scatter, so positive direction, and, you know, little scatter, strong relationship. All All right, and as the amount of scatter increases, the correlation, you know, gets a little bit closer to 0. I'm just kind of ballparking this. We might say r is equal to 0.6, whatever this is. Okay, x and y. So you know, I'm just kind of eyeballing this, and we still have, but still positive direction, right? Positive, you know, kind of a moderate relationship. Moderate strength relationship. All right, until you get to a point where there's just a ton of scatter, and you have no real predictive power. And knowing x doesn't really tell you anything about y. So perhaps we have someone's height and maybe their SAT score. And here we would expect r is equal to 0, okay? Because you can have, knowing how tall someone is probably not going to give us any information about the person's SAT score, okay, or GPA or something like that, right? Two numeric variables that are not related. So here we would say no relationship between x and y. Is that okay? And then, you know, there's more examples on page 149 and 150 in the book. And they show, you know, examples. Maybe I'll show like 1 or 2 examples for negative trend. So now we have negative direction. I'm going to just kind of eyeball this, maybe negative 0.8, okay? Negative direction, some scatter. But, you know, not too much. Between x and y. Is that okay? All right, so let's just double check our understanding here. Okay, so these are all supposed to be in a straight line. What is the r in this case? Positive 1, right? Okay. What is it in this case? Okay, also 1, right? So even though, so the slope does not affect r, okay? Okay, so this is steeper and this is less steep, but r just tells us the direction and the strength. R is only influenced by the direction and the strength, and in both cases the strength is, you know, perfectly strong. This is supposed to be flat. What do we have here? R is 0. It's neither positive nor negative, okay? Okay, it looks like a straight line, but it's really, we're just getting the same value of y, okay? So it's kind of, it's like asking, is someone's height related to the number of fingers they have on their hand, okay? So I realize not everyone has 10 fingers, but, you know, maybe everyone you asked, maybe you surveyed 50 people, and all 50 people had 10 fingers on their hands, would you find a relationship between the person's height and the number of fingers on their hand? No, there'd be no relationship, right? Everyone's going to have 10, so you're going to have neither positive nor negative relationship. Okay? And then, but, you know, as soon as it kind of ticks downward, this is supposed to be a straight line. You have -1, okay? So negative direction. Negative direction and no scatter. Could be, yeah, number of fingers. And height. Something like that. Okay. Are there any questions on this? Okay, and so this is correlation coefficient. Let me write down a few, kind of a few key conceptual points about correlation. Conceptual points. Okay, so the order of the variables does not matter. Okay, so if the correlation between x and y is, you know, 0.78, then the correlation between y and x is also 0.78. Okay, so switching x and y does not affect correlation. Okay, let me ask you a question. So, assuming we're talking about heterosexual couples, male and female, do you think there is a correlation between the height of the male and the height of the female? Yes, no, maybe? Okay. So,
Yes.
I think so you guys are saying yes. Okay, so some of you, when you first hear that, you might not think yes or no, okay? But if you switch the variables around and I say, is there a correlation between the height of the female and the height of a male? Okay, again, assuming we're talking only about heterosexual couples, if we think about it, there's kind of this general trend where if, and of course there's exceptions, and so probably the strength of this relationship is not very strong. But overall, we'd probably see a trend where many women will be in a relationship with a male who is taller, or we could flip it around and say many men will be in a relationship with women who are shorter. Of course, that's not always the case, but overall, I would say there's a trend does exist between the height of the male and the height of the female, okay? Just looking at the broad population. And of course, anytime I talk about general trends, I have to say there's exceptions and we're only limiting ourselves to these populations. But, so if we do see a correlation between X and Y, we're going to see the same correlation between Y and X, okay? Okay, let's see. Multiplying by a positive constant or adding a constant will not to one or to one or both variables will not affect the correlation. Okay, so maybe kind of practically speaking, it means, you know, changing your units will not affect correlation. So kind of on a practical level, changing units okay, so if we look at the weight of someone and their height, okay, we can measure the person's height in inches, and we might see a correlation of 0.7 between someone's height and their weight, okay? We can measure the height in centimeters, and the correlation will remain the same at 0.7. So changing from inches to centimeters, or pounds to kilograms, or Celsius to Fahrenheit, or, you know, whatever the unit is, you can measure someone's salary in dollars, or you can measure their salary in thousands of dollars, or you could change it over to euros or whatever it might be. Changing the unit will not affect the correlation, okay? As long as you are consistently applying this change of adding a constant or multiplying by a positive constant to the units, okay? Or not the units, to the variables. Okay. The correlation itself, R itself, is unitless. It has no units. It's just a value between -1 and +1. Okay, and again, the usage of R, or the interpretations of R, only make sense if the relationship is linear. Okay. Are there any questions on this? Yes?
Is there an example where multiplying by a constant, if you used a negative constant, where this wouldn't work?
Yeah, so if you multiply by a negative constant, it will just switch the sign of R. So R will go from, if it's the correlation is positive 0.7, and you multiply by a negative constant, then the correlation becomes negative 0.7, okay? Because multiplying by, like if you just multiply everything, like if you have this, then multiplying by a negative constant would suddenly turn it into this, okay? If we multiply by a negative constant. So you know, when we're talking about multiplying by a constant, it only makes sense when it's a positive constant. Okay. So maybe example would be, you know, we could say, you know, is there a correlation between the number of hours studied and someone's test score, okay? And we might see a positive correlation where people who studied more got higher exam scores, and people who studied less got lower exam scores, okay? We could say, is there a correlation between number of hours studied and the number of questions a person got wrong, okay? Going from a test score, a percentage, to figuring out how many questions the person got wrong is actually a simple calculation. You just have to figure out how many tests problems there were, and then you just multiply or divide by that number, okay? But it's a negative thing, because now we are trying to figure out how many questions someone got wrong. And so the correlation would actually be the same, but it would switch signs from positive to negative. We'd see negative correlation between hours studied and the number of problems gotten wrong. Is that okay? All right, why don't we take a short break here. We'll get started at 8:50. I'll get started at 8:50, and so we'll continue on.